All right, welcome to physics video 7.3. We're going to learn about Newton's law of universal gravitation. And hopefully this video will make it clear why we spent the last two videos learning some math skills. All right, objectives are up on the screen here. I'm not going to read through them. Write them down if they are useful to you. Definitely take a second to read them. All right, so Newton and the apple. So here's the deal. Isaac Newton, you may be familiar with him from Newton's laws, was hanging out one day thinking about the moon. All right. And so he was picturing in his head this idea. So he knew that the Earth was the planet where he and all his friends lived. And he knew that the moon, that's the moon right there. He knew that the moon orbited the Earth, right? He knew that it went around and around and around in a circle, right? And so, knowing his own first law, he knew that an object in motion wanted to stay in motion. And that if there was no force on the moon would follow this green dotted line and it would float away, right? So, because that wasn't happening, because the moon wasn't floating away and going in a straight line, he realized there had to be some sort of force pulling it inwards, right? To keep it moving in a circular path, right? We talked about this when we did centripetal force, right? Something's going in a circle, there has to be an inward force. So Newton recognized this, but in his day, nobody knew what that force was. So as the fable goes, he was supposedly hanging out one day looking at the moon, which is up here, thinking about it, when suddenly an apple fell out of a tree bloop, and hit him on the head. And he said, ouch. But he also said, eureka. And he realized that the same force that pulled the apple down, gravity, is also the force that pulled the moon down towards the Earth, right? So that was a huge breakthrough. And he said that, you know, the apple is attracted to the Earth by a gravitational force, so maybe the moon is attracted to the Earth by that same force, okay? So then the question becomes, well, why is the Earth so special? Why is the moon and the apple and everything else attracted towards the Earth as opposed to some other object? All right, sorry, phone ring. So he was wondering why the Earth was so special, why objects were attracted to the Earth as opposed to some other object. And so he realized that there isn't anything special about the Earth. And he realized that any two objects are pulled together by a gravitational force. What separates the Earth from most other objects is that the Earth has a tremendous amount of mass. Okay, and he realized that that must have something to do with it. So he ran some extra experiments, did some thinking, and he came up with Newton's universal law of gravitation. And Newton realized that the force of gravitational attraction between any two objects, all right, remember, I think I have not stressed this enough so far, that any two objects are going to be attracted to each other by a gravitational force. And how much force there is depends on the mass of the two objects. More mass means more force, right? In math speak, it's this. The force of gravitational attraction is directly proportional to the mass of each of the two objects. So in other words, if you've got twice the mass, you're going to have twice the force of gravity. Okay? So, for example, well, I'm getting ahead of myself. Okay, so there you go. The mass is directly proportional to the force of gravity. Okay? He also realized that the distance was important. Okay? And that relationship turned out to be a little bit more complicated. But it turns out that the distance between the two objects' centers was important. And the force of gravitational attraction between the two objects is inversely proportional to the distance squared. So that's an inverse square relationship, which was the whole point of the last two videos you watched. All right, so it turns out as your distance increases, if you multiply your distance by something, then the force of attraction between them gets divided by the same number squared. Okay? Please remember that the force of attraction is the same on both objects. All right, so if you've got object A, which is maybe the Earth, and object B, which is maybe a ball, the Earth pulls the ball down with just as much gravitational force as the ball pulls the Earth up. The only reason we don't notice the Earth moving is because it has such a tremendous amount of mass. Okay, so Newton eventually came up with this equation. And he said that the force of gravitational attraction between any two objects is equal to a constant, which he called g, it's the universal gravitation constant, times the mass of your first object, times the mass of the second object, divided by the distance squared. Okay, so g is your universal gravitation constant. It's this magic number, kind of like pi comes up with circles anywhere in the universe. This universal gravitation constant, 6.67 times 10 to the negative 11th, comes up anytime you're solving gravity problems, dealing with force and the mass of the two objects. Okay, so M1 and M2 are the masses of the two objects, and then D is the distance between their centers, like I said in the last slide. So let's jump into it and do a couple problems. We're doing on time. Oh, awesome. This is going to be the shortest video ever. All right, so your weight on Earth is an example of the force of gravitational attraction. Check it out. So here's the Earth. Here's you. Hello. Okay, so if you wanted to find the force of gravitational attraction, you would need to know your mass, which, for the sake of argument, will be 70 kilograms. You would need to know the mass of the Earth, which I happen to know. How they measured this is actually fairly complicated. And if you want to know, you can come in early or stay after school one day. But the mass of the Earth is in the ballpark of 5.98 times 10 to the 24th kilograms. And then remember, D represents the distance between their centers. So it's the distance from your center, your belly button, to the center of the Earth, which for all intents and purposes is just the radius of the Earth, right? So it turns out that the radius of the Earth is 6.38 times 10 to the 6th meters. Okay, so there's our two masses, there's our distance. We know G, whoa, we know G is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared, and plug in your numbers. So after you plug in your numbers, here's what you get. 6.67 times 10 to the negative 11th is our G. The masses are 70 and 5.98 times 10 to the 24th. Your distance is given to you. So plug it all into your calculator, and you should get 686 newtons. Oh, 686 newtons. All right, so there's your force of gravitational attraction. Now notice, there's another way we could have done this. You may remember from first chapter, or from first trimester, that your force of gravity is equal to mass times the acceleration of gravity if you're on Earth, right? So technically, well, the mass is 70 kilograms. Technically, acceleration of gravity on Earth is really 9.8, right? We always use 10 just to keep it simple, but and if you multiply this out, you get 686 newtons, right? So we're happy. So the question is, well, why on Earth would we ever use this equation to find our force of gravity if this one does it much more easily? And the answer is, this equation here only works on Earth and if you're at the surface of the Earth, okay? Because think about it, what if we built a tower that was super tall and you stood at the top of the tower? That's going to increase your distance, right? Which would change your force of gravity. Or if you're on a different planet, Mars or Saturn or something, then there's different gravity there, okay? Regardless, though, of where you are, this constant remains the same, okay? So here's another example. It's almost the exact same thing, but I just want to point out that it works. You could find the force of gravitational attraction between you and the pen that you're writing with right now. Okay, so what you would do is you'd use the force of gravity equation. The two masses would be your mass, 70 kilograms, and the mass of the pen, which is maybe 0.05 kilograms, and then D would be the distance between your center and the pen's center, which is somewhere in the neighborhood of 80 centimeters or so, assuming you are holding the pen in your arm, or in your hand rather. So take a second, plug the numbers in, and see what you get. So when you plug your numbers in here, you get these guys. I skipped the units to keep things simple. Plug it into your calculator, and you should get that. Cool. So final example, we can also work backwards. In this one, it says, how close would a 70 kilogram physics teacher be to a 6,000 kilogram, oh, somehow I deleted the word elephant. It's supposed to be 6,000 kilogram elephant. If the force of gravitational attraction between them is 8 newtons. So we're going to work backwards. All right, so I'm going to actually do the algebra first. So start with this equation. You know our force of gravity is this. So if you want, you can plug in your numbers and solve for d. I'm going to do the algebra first. If we multiply both sides by d squared, you get this. So we're still trying to solve for d. So we got to divide by force of gravity. That gives us d squared equals g m1 m2 over force of gravity, and then take the square root of both sides. Okay, so from here we just plug in our numbers. So you're going to get 6.67 times 10 to the negative 11th times your two masses, which would be 70 and 6,000. Divide that all by your force of gravity, which is the 8 newtons. Don't forget your square root, and you get, oh, that's not what I wanted to do. .0019 meters, which is what, about 2 millimeters. So for a physics teacher to get that close to the center of an elephant, something really gross would have to happen. So, so I apologize for that image. All right, so there we go. I think that's it. I actually realized I do need to do one other quick thing, which is this. Sometimes I'll give you a problem like this. So suppose we had two objects. Suppose we had object A and object B. And I told you that they were attracted by a gravitational force of whatever, I'm going to make up a number, 8 newtons. Okay, so there's our force of gravitational attraction. You should be able to tell me what the force would be if, for example, the mass of object A doubled, or the distance between them was cut in half, or whatever. So let's do that. Let's suppose the mass of A doubled. Well, what that means is one of your masses gets multiplied by 2. Remember, your force of gravity is proportional. So that means that your force of gravity is also going to get multiplied by 2. So if you doubled the mass of object A, then your new force of gravity would be 16 newtons. Okay? Or what if you moved them so they were half as far apart? If they're only half as far apart, then we're taking our distance and dividing it by 2. So that means that our force of gravity, remember, distance and force of gravity follow the inverse square law. So if our distance got divided by 2, then our force of gravity is going to get multiplied by 2 squared. So you'd take the 8 newtons and multiply it by 4, will give you 32 newtons. Okay? So, there you go. Cool. Short video today.